Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the 13th lecture on the course Marine Renewable Energy Systems, where we are going to discuss about the analysis, design and development of renewable energy systems. The primary focus is on wave energy converters. We will also discuss something about the wind farms and the development of those structural systems in this course. So we are discussing about the development from the fundamental procedure of design of a floating wave energy converter in the previous lectures. So in this lecture number 13, we are going to continue with the discussion what we had in the previous lecture, where we will talk about further development and discussions on floating wave energy converter. So welcome to lecture 13, sequel lecture number 3 on design and development of floating wave energy converter 3. So friends, let us wind back and see what was the equation of motion we had in frequency domain. So your floating device In our case, it is a floating wave energy converter. which will have 6 degrees of freedom, can be represented as follows, which we already wrote in the last lecture, but for continuation: omega square m x hat omega should be, the inertia component should be equal to f e omega plus f r omega plus f h omega plus f p t o of omega plus f m of omega. We call this as equation number 1 for the local lecture number. However, the equation is continuous from the previous lectures, therefore the numbering has to be very carefully handled. Now, in this above equation, let us say m yeah, it is not working. Sometimes it works, sometimes it does. There is a, let us see. Okay, I'll see. Okay. So, in this equation, m denotes the total dry mass Since it is 6 degree of freedom, we should say specifically it is dry mass matrix. X hat is the complex displacement quantity or a complex displacement vector of order 6 by 1, which has got both the translational and rotational degrees of freedom displacements. Okay. Fe is a linear excitation force. Fr is a linear radiation vector. Fh is a linear hydrostatic force vector. And Fpto is a force vector for linear damping. Friends, this is a very important aspect in the design. We are now considering only a linear damping as a virtual damping figure in the frequency domain. Therefore, we call this analysis level as primary analysis. Okay, and Fm denotes the mooring line force vector. In this example, this is actually a taut mode system. So, accordingly, there will be an initial axial stiffness applied to the system. So, that will be included in this vector. So, now this equation represents the motion characteristics of the floating device in all 6 degrees of freedom. Now, we know that this system is position restrained by tethers, and the force matrix represents both forces and moments. Okay, this force vector represents both forces and moments corresponding to respective degree of freedom. If it is translational, they will be simply forces. If it is rotational degree of freedom, they all will be moments. Having said this, in the original design, to start with, we consider that surge motion as a strong coupling and response of the device, because the device is freely floating and out for a unidirectional wave. Let us say this is the device, for a unidirectional wave when the device is freely floating. Therefore, this motion, okay, will be predominant. In translation degree, the motion along sway will be very limited because it is a unidirectional wave. The motion along the sway direction will be less predominant because we are considering unidirectional wave at this moment. And of course, in the heave degree of freedom, the system is position restrained. Okay, in heave motion, the system is position restrained by taut mode tethers. Okay. Now, these are all the bean shaped floats. This one as well as this. And this is the central buoy, which we call as CB. Now, when you start applying the wave force excitation to this system, the central buoy, which is freely floating, which is anchored to the seabed, by a taut mode system, will always have a free floating phenomenon. Okay. Therefore, the central buoy will undergo initial set down. What is initial set down? When the wave is acting, the buoy will start moving or oscillating about this position, correct? So, we call this as initial set down, and we also call this as initial offset. So, the buoy is a freely floating element, therefore, the buoy will undergo initial set down and initial offset, and from this position the device will start oscillating. Okay. We should also notice that the surge response of the whole device will be controlled significantly by the mooring lines, because mooring lines will enable recentering process of the device. So, the mooring lines will not allow the central buoy to move beyond certain limit. For example, in the screen let us see, if the central buoy wants to take this position, it cannot happen because these cables are inextensible. These cables are inextensible. Okay, let me write it in a different color. So, the movement of the central buoy is restricted to certain band. So, that is the control which is offered to the whole system by the mooring lines. Therefore, we can expect that there is a very strong coupling between surge and of course heave. Surge is seen as offset and heat is seen as set down. Furthermore, friends, the pitch motion, that is a rotation, can also be affected because there will be a differential settlement offered by different phases of these moving lines, and this differential settlement can also invoke marginal pitch. However, for a unidirectional wave, surge, sway and yaw modes cannot radiate waves. So, therefore, surge, sway and yaw modes will not generate or let us say radiate waves. Why this is? Because the floats are symmetrically arranged. So, if this float starts giving you, if this float starts moving in this direction generating radiation waves here, this float will also recenter and compromise that effect. So, the radiation effect of the waves in surge motion, in sway motion and in yaw motion will be minimum. Therefore, the device motion or the device response, in these degrees of freedom is not useful in harnessing the wave energy. Because these are referred as wave free modes. So, my PTO should encounter or accompany only those modes where the energy can be harvested. So, interestingly, Wu et al. Clearly pointed out this discrepancy in his study. Therefore, to put a note here, the device is effective in capturing the wave energy only in, let us say, heave or equivalent pitch mode, because of differential settlement happening, and of course, in pitch mode the hardness is higher than other degrees of freedom. What are the other rotational degrees of freedom? For example, yaw and roll, pitch will be higher. So, therefore, friends, my power takeoff mechanism should be designed in such a manner only to address a specific mode of vibration, which is this. In other words, for a unidirectional wave or for wave acting along x axis or x direction, any floating body like this device can invoke only 3 degrees of freedom. What are the degrees of freedom? Surge, heave and pitch. Let us look at this if this is my body and these are the axes as x, y and z, we know along x it is surge, along y translation it is sway, along z translation is heave, and about x it is roll, and about y it is pitch, and about z it is yaw. So, for a unidirectional system only surge, heave and pitch will be active. Okay, they are only active innovations. Therefore, when the float encounters a pitch motion, it induces the relative heave in the central ball, is it not? We already saw that. If I say I have a central buoy and I have the bean shaped floats attached to the central buoy by the connectors, when there is a pitch motion, the central buoy will also have a heave motion, because we already said the heave and pitch are coupled because of differential heave. We call this as differential heave. Surge and heave are anyway coupled, they are called as offset and set down. In addition, they are also coupled because of differential heave. So, we must be able to harvest that clearly. So, the central buoy now undergoes two coupled motion, one is heave, other is pitch. So, now let us see amongst these two, which are we going to harvest? So, these two motions, these two response quantities are sufficient to express the working principle of the wave energy converter. Amongst these two, since we know they are coupled to each other, we are talking about independent degree, therefore, any one of them is sufficient to represent the response quantity. Okay, any one of them is okay, and that is the degree of freedom which is used to harness. As I said, we want to tune the frequency. So, we want to identify the fundamental frequency at which the tuning has to happen. So, the tuning is between the excitation frequency and the fundamental frequency. So, out of all 6 degrees of freedom, 1, 2, 3, 4, 5 and 6 degrees of freedom, which degree should I tune to this wave? Okay. So, we can either choose heave or pitch. So, we prefer to choose heave. So, one can easily tune this. Okay. So, that becomes easy for us to tune it only for 1 degree. So therefore friends, when the device is moved, then the surge and pitch coupling becomes minimum. Because it is not freely floating in surge, it is moved, and this freely floating in surge axis to some extent will not invoke pitch. It will not allow the body to rotate about the y axis. Pitch is rotation about y, is it not? Pitch is rotation about y. See here. So the body freely floats in surge to some extent, not infinitely, but it will not allow the body to rotate about y. Okay. So the coupling between the surge and pitch value remains minimum. So therefore, the individual rotation what are the individual rotations we have? R, y and minus theta of the float about where do they happen? These floats are anyway connected to the central buoy. Therefore, all these motions are happening with respect to the central buoy, is it not? Because it is connected to the central buoy. About the central buoy should be now externally damped. Why do we need to damp this? If you do not damp this, you cannot harvest energy. If you do not damp, it will be freely floating. You have to apply damping and to get the energy. Okay. So, you apply damping and this is done by an external PTO. And this will help me to extract the wave energy. So, therefore, our interest now is limited to the relative motion between the floats and the central buoy, correct? And that too in the net heave direction. In the net heave direction. This is our catch of the design now. So, therefore, I can now represent this in the equation of motion as follows. Therefore, the equation of motion is now modified with the above discussion. So, minus omega square m z hat omega. Okay, instead of x hat omega, I am replacing this with z hat, that is heave motion, that is equal to f hat, the Frau-Krelov force, the complex quantity, plus f hat, the complex quantity of the diffraction force, plus the complex quantity of the radiation effect, plus the complex quantity of the hydrostatic force, plus the complex quantity of the force vector of the PTO coming from damping, plus the complex quantity of the force coming from the mooring line. I call this equation number 2. So, now this is the equation. Now, I can say friends, this equation 2 is the equation of motion in the active degree of freedom. Though the system has 6 degrees of freedom, but we are slowly ignoring the rest of them and picking up only the most active degree to which I am going to use the system for harnessing the energy. Okay. So, I think nevertheless we can still write for our understanding the z hat quantity is the complex amplitude response in heave, okay, where m is the mass of the individual body. Now, the force terms on the right hand side of this equation is a combination of varieties of forces. Therefore, the total force generated due to water pressure is the sum of hydrostatic and hydrodynamic force. So, the total force generated will be the sum of hydrostatic and hydrodynamic force. Okay. External forces may also arise from other sources. What are the other sources we have? It can be due to drifting, it can be due to current, it can be arising from drag, it can be also internal friction, is it not, between the moving bodies. So, we neglect all of them in the formulation. Okay. We make one more assumption. We say that the seabed, though as per the bathymetry may not be horizontal and smooth, but seabed is considered to be smooth. Why do we assume this? Because if we do not assume this, then the water depth continuously varies. We want to keep it uniform so that water depth remains constant and we ignore the bathymetry effect. Bathymetry relates to the sea surface elevation, the undulation of the seabed, okay, is neglected. Bathymetry effect is neglected. So, therefore, friends, we have now represented the motion in a generic form considering heave as an active degree of freedom. Therefore, z dot and z double dot all will be displacement, velocity and acceleration. Let me write it clearly. Acceleration in heave degree. So, remember friends, when I say heave, I am talking about the relative heave, okay, between the floats and the central one. Now, let us talk about the friction or the damping force. Let us talk about the damping effect. The damping effect is a virtual damping applied to the PT. If you do not apply damping, you cannot harness energy, okay, because the body will be freely floating. If you want to really find out, in mechanical engineering also, when the wheel is rotating, let us say the wheel is rotating, you want to find the horsepower, how much horsepower is produced by the rotation of this motion. We call something called brake horsepower. We apply a frictional brake to this. We apply a frictional brake to this and then try to measure the power. So, wherever you want to measure any power or energy, you have got to apply a damping effect to it to measure the energy. So, similarly, in wave energy device designs as well, we need to apply something called virtual damping to the system through PTO to harness the energy. Okay. Let us see how do we represent this. Let us say this is represented as follows. F hat R omega is the radiation damping, okay, is given as minus I omega, the radiation damping coefficient Rd of omega, function of frequency of the displacement, plus omega square A m omega z hat w. So, obviously friends, this component will be velocity and this component will be acceleration of z hat. Okay. So, we call this as equation number I think 3 in this local line. Now, in the above equation, C omega, that is C radiation damping of omega, is the hydrodynamic damping coefficient. Coming from the sources. What are the sources of this damping? It comes from two sources. One is a viscous effect, other is a radiation. But amongst these two, the radiation effect will be more dominant than the viscous. Therefore, I represent this or love to represent this as CRD. Okay. So, we ignore generally the viscous effects. Therefore, C omega is generally written as CRD of omega. Okay. And AM represents the added inertial coefficient. Where this come from? What is the source for this? It comes from the added mass. How the added mass is invoked? When the central buoy connected to the seabed heaves. Okay. So, the water level does not remain static, it keeps on changing, is it not? So, the added mass coming from this part as well as this part, sometimes it can be the other way, that the added mass can also be this part. So, all these contribute to the added mass effect. So, I get that value in this equation here. Therefore, friends, the hydrostatic force which I call as F hat of omega represents the restoring force in buoyancy, sort of a stiffness. Okay. Here the restoring force comes from the stiffness, it comes from the stiffness of the system at still water level. Now, this will be a function of heave displacement, isn't it? So, I can say now the heave displacement is Re of z bar omega of Ei omega t, Ei omega t. Equation number 4. The mean vectored surface which will contribute to the added mass effect is referred as S or AW, which is given as, so F hydrodynamic force of is minus KH Z hat omega, which is also said as minus rho G AW Z hat omega. Okay, fundamental principles of physics. So friends, let us come to the summary of this lecture before we continue to do this discussion further in the next lecture. In this lecture, we started discussing about the equation of motion of the floating wave energy converter with 6 degrees of freedom. Then we understood that amongst the 6 degrees of freedom, only 2 can be activated for unidirectional wave. Essentially there are 3, but surge is ignored, heave and pitch can be activated. But since heave and pitch are coupled, we are looking for independent motion, I can now say heave is the predominant degree of freedom which need to be tuned. So then we moved on this equation effectively to effective equation of motion, which represents heave degree of freedom, and it is relative motion between the floats and the central body. Then we started understanding what is the necessity of applying a damping to the PTO to harness energy. So friends, the summary what we have in this lecture, I hope you have gone through them very clearly and you will be reading the previous lectures for continuation purposes. Stay connected with us, we will take it forward to discuss more in detail about this analysis and then move on to the experimental methods of this particular design and try to find out experimentally how this was designed and how it was optimized to get the maximum efficiency of energy harvest. Stay connected. Thank you very much. Namaste.